Okay, so for this first episode of Papers in a Pinch, I'm going to be talking about a paper titled Koopman-Assisted Reinforcement Learning. Please go check out the authors and their affiliated institutions in the description. Of course, the link to the paper as well. So I'm going to just give a kind of brief background to reinforcement learning itself, just provide a bit of context there. Some of you probably already know this, but just in case you don't. And throughout these episodes, sometimes I'll just kind of return to the basics, kind of lay that foundation out. But then I'll pretty quickly get into specifically what the paper is doing that's different beyond kind of the normal approach, right? So reinforcement learning is one of the three types of machine learning, three main types anyways. You have supervised learning, which is kind of your standard approach where you're using data that have labels in it. And you use those labels to essentially learn a mapping from inputs to outputs. You have unsupervised learning, which has no labels in the data. It's kind of take that raw data, try to find the inherent structure, the patterns, where things are grouped, where things are clustering. And reinforcement learning is quite different. Instead, you kind of put an agent into a realistic environment. That agent interacts with the environment, and then it gets feedback. So it's pretty similar to how you can imagine humans doing a lot of their learning, right? We would first go into an environment pretty naively. We'd interact with it. We'd use that feedback, kind of like rewards and punishments, if you will. And that feedback would help us learn a better kind of internal model about this environment that we're operating in, okay? In the case of AI, the reinforcement learning tries to essentially learn what is called a policy, and that policy is telling you how to act in any given situation. So if this is a self-driving car, reinforcement learning would make a lot of sense to use here because you don't have a lot of labeled data. You're not going to have a bunch of data that says, on the street with this stop sign, on this corner when somebody does it. There's too many things that could go on in the situation to use labeled data. The reinforcement learning makes a lot of sense because it's going to have some familiarity to that environment, but it needs to be able to take actions with a decent amount of uncertainty there. And so it's essentially based off of an MDP, a Markov decision process, which just means you have a set of sequential steps that take place and you have transitions between those steps. And reinforcement learning kind of models the situation, if you will, as an MDP, and then tries to find a policy that allows you to act in those sequential steps effectively. It has the Markov property, which means it's memoryless, which just means you're not using a bunch of history to make the decision. You're kind of just using the current situation. And as a machine learning approach, that makes sense for something like self-driving cars or playing Atari or something where you're going to be in an environment and you just don't have a lot of historical data to base it off of, but you still want to have a good model or policy to know what action to take. There's lots of uncertainty here, but there's still a lot of pattern and structure, if you will, that you can leverage, right? Anyway, so that's reinforcement learning. And what these authors do in this paper is they augment one of the core parts of reinforcement learning, kind of in the kernel or the core of it, which is called the Bellman equation. The Bellman equation essentially works iteratively to learn what's called a value function. And that value function is essentially saying, how good is this state that I'm looking at? So if it's a chessboard and you're looking at all the pieces on that chessboard, what's the best action I could take right now? What is the value of a given action in that state? If it's, again, self-driving vehicles, right? You got an intersection and you got somebody swerving here, or whatever that situation is, that's a certain configuration. What is the value of the different actions I could take, or what is the best possible? You're essentially trying to maximize the cumulative reward. If you think about an agent acting in an environment and getting feedback, that feedback can be thought of as a reward. You're trying to maximize that cumulative reward over time, which is really just saying, what's the best action I could take at any given time? Okay. And the Bellman equation is sitting at the core that's helping kind of build indirectly this policy that's going to tell you how to get the best action at any given time, if it goes well. The thing with the Bellman equation is it kind of comes from originally more kind of traditional optimization and things like that. It doesn't scale that well. So in a lot of more realistic situations, which are going to be much more complex, a lot more factors involved, a lot more nonlinearity, it's going to be hard to scale something that can't account for all that complexity. And the Bellman equation is essentially like that. If your problem is smaller, the Bellman equation is going to work pretty good. If your problem is categorically hard, right? So you can imagine going from a chessboard to something like an Atari game or self-driving vehicles, which is much more realistic. It's just going to be hard to make that Bellman equation quite tractable, or the overall reinforcement learning approach. So the authors in this paper are going to do something to this Bellman equation essentially, and its associated value function, to augment it, to make it more scalable, to make it more conveniently calculable, if you will. And the way that they do this is using the Koopman operator. So the Koopman operator is something from mathematics. It's a mathematical framework that essentially takes something that's hard and complex and makes it linear. Okay, and this is a very common approach in science. Is, a lot of things in the real world are just not analytical. They're very hard to calculate exactly. Of course, we have to make approximations. One of the most common, probably the most common way to approach this is to try to make the system linear, right? So it's a lot easier to add a bunch of things together than try to, pick apart and decode this convoluted system that's got all these nonlinear dependencies and, cause and effects that work in ways that we just don't know. So if you can make the system linear, it will go better. So that's what they're doing with the Koopman operator. Just briefly, the Koopman operator as a mathematical framework essentially uses this notion of infinite dimensions to take observables. So you can imagine these would be something like basis functions. So again, just stepping back foundationally here, imagine you've got some situation. It's very realistic. Again, maybe a self-driving car. The environment's got just countless, for all intents and purposes, variables involved. And the dynamics is extremely convoluted, right? It's very hard to understand exactly. In fact, you can't understand exactly what the dynamics of that situation are. There's no way to kind of express that analytically or exactly as an equation. It's very, very opaque. And so you kind of raise the level of abstraction and you might form like things like basis functions, which are kind of higher level functions, if you will, that kind of summarize the dynamics of what's happening. And so if you run into a very realistic situation, I'm going to create these kind of higher level basis functions that are kind of one step above the true core nonlinearities of the system because they're just easier to work with. And then you can do things with those basis functions. And one thing you could do is put them in a Koopman operator, which basically says I can take those basis functions and add them together. So I can make it linear. It's much easier to work with the system. And of course, the idea there is that if we can recast this nonlinear system into kind of a linear representation, that I'm still preserving the true dynamics of the system, at least to a reasonable extent. And that would be the reason or the argument you would use to actually use something like the Koopman operator. So it's a mathematical framework. It's got this infinite dimensions. There's lots of room to play around with. And that flexibility affords it this ability to take dynamics of a very complex system and make them linear. So we can add them together. So because of that, it's much more scalable. And when you get scalability, you can handle more complex environments. You can have a lot more data coming in and so forth, which is always the case with AI. Okay? So really briefly, let's do a quick recap because we still got more of the paper to talk about. But reinforcement learning is one of the main types of machine learning. You got supervised, unsupervised. Reinforcement learning is an agent interacting with an environment in a very realistic fashion and using that feedback to essentially build a policy which will tell the approach, the model, the system, which action to take at any given time. So very realistic real-world situations can definitely benefit from things like reinforcement learning. Of course, you got to learn that policy. And part of doing that is this thing called a Bellman equation. That Bellman equation tries to essentially iteratively learn this value function, which will tell you the value of an action in any given particular state or configuration of the system. But that equation alone is not that scalable. It doesn't handle real-world situations that well. There's too many factors involved. So to make it more scalable, you need something that's going to, in this example, make it more linear. Because linear things scale a lot better than nonlinear things, right? For obvious reasons. They're more additive, so forth. So to make that Bellman equation scale better, they're going to use this mathematical framework called the Koopman operator. That's going to make things additive. That's going to make things more linear. And now you can kind of augment essentially the Bellman equation in a way that it scales. If it scales, you can place reinforcement learning into more realistic situations. Okay, so I hope that makes sense. So they're going to use the Koopman operator. Now, the way that they use the Koopman operator is they actually fashion a Koopman tensor. And a Koopman tensor just goes one step further and essentially parameterizes the Koopman operator with control actions. Control actions are essentially when we take an action in an environment, the environment itself changes, right? So you could be looking, maybe the environment is a chessboard, and the state or the configuration of that system is all the positions of those chess pieces. But if I go to move a chess piece, which of course I will, now the configuration changes. Now the state changes. So it's much more realistic if you could incorporate this kind of additional information into the mathematical framework of the Koopman operator. This additional information being these control actions. The fact that it's not really a static environment, it's changing as the agent interacts with the environment itself. And so that's what they do, is they take the Koopman operator mathematical framework, they take these control actions and they parameterize those into the Koopman operator to create a Koopman tensor, so like a higher dimensional kind of form of the Koopman operator, if you will. And now it's just much more realistic. Okay. And now they've got this Koopman tensor. which is sitting on top of or part of the Koopman operator framework, which is how they're augmenting the Bellman equation, which is at the center of reinforcement learning, which now means we can go do reinforcement learning much more realistically and in larger, more complex situations. Okay. And that's essentially what they did. And so then they specifically apply that to these kind of max entropy equations, which are kind of ways to kind of fold the Bellman equation, the value function, everything together, kind of package it up into the AI system and actually implement it. You have things like soft value iteration. So again, you're doing things iteratively with that Bellman equation to get that value function. Softness is coming from the entropy term. You kind of regularize the system using entropy. The reason you do this, which is true, again, in a lot of modeling approaches, is you incorporate entropy to encourage exploration. So you're trying to make it more realistic by exploring more possibilities, right? Again, as that Bellman equation and as that kind of value function iteratively gets built, you're trying to understand what the best action is to take at any given time. You typically get kind of a distribution of action state mappings, if you will, or different possibilities that you could take as the configuration of the system changes. You kind of get a distribution of over all those possibilities, or a great number of those possibilities, and then just probabilistically try to choose the best one, right? So anyways, part of doing that, and this is a big part of reinforcement learning in general, is to try to encourage both exploration and exploitation, right? Exploration is you're going to move around the possibility space that much more. You're going to run into fortuitous things. And of course, exploitation is once you find something good, you try to fold that in this case, into the policy to make sure you hold on to it, right? So the entropy in these soft value iteration type approaches is kind of regularizing or putting something into the approach that makes sure you're encouraging a decent amount of exploration. There's also the soft actor critic architecture that they'll use, and it's kind of beyond the scope to get into all the differences. But again, taking reinforcement learning, going to the Bellman equation, augmenting that Bellman equation so that it's much more realistic by using the Koopman operator frameworks, more specifically the Koopman tensor, and allowing it to be parameterized with these control actions and making the whole thing much more scalable, because now it's essentially a linear system that is hopefully preserving the true underlying dynamics. And they put it into these soft actor critic architectures, or these soft value iteration approaches, these kind of max entropy style, which is just a normal thing to do with reinforcement learning, right? If you wanted to benchmark something and see how the improvement is, you would put it into equations like this, or algorithms rather like this, to see how it performs. So they do that, and you can go check out the paper, and you can see the benchmarks that they were able to pass, and some of the promising avenues that this approach seems to take. And they have like these 4 examples of realistic situations that are, reasonably complex, reasonably categorically hard. And it shows that the reinforcement learning approach seems to work quite well. And so that's it. So I'll just do one more quick recap, and hopefully that made sense. This is the first episode. Please give me your feedback. Too difficult to understand? Not difficult enough? I try to keep things very conceptual. Again, you can obviously go to the paper yourself and take a look at the equations and dig in deep. I don't want to do the whole reading of the paper for you. That wouldn't make sense. But definitely want your feedback in terms of, is this valuable to you, so that you can keep up to date on the latest research. Let's just do one more recap, and hopefully you can see how this all comes together. Again, this is in the area of reinforcement learning. Agent interacts with the environment, gets feedback, does that iteratively again and again and again until it builds a policy which will tell it which action to take at any given time. Self-driving cars, playing Atari, maybe a chess game, you can see how this would make sense. Quite similar to how, seemingly, humans learn as well. At the core of that reinforcement learning approach in AI is something called a Bellman equation. It essentially iteratively tries to build a value function, which is telling you the value of any given action at a given time, given the configuration or the state of the system you're looking at. So if you jump into the chessboard, or you jump into the road with your self-driving car, you want to know which actions to take, right? So all of this is done to essentially build a policy so you know what action to take at any given time. But that whole approach, that standard approach to reinforcement learning, is just not that scalable. Doesn't deal with a lot of realistic situations where you got tons of factors. By far, the most common way in science and technology to make something more scalable is to try to make it linear. This happens across all kinds of domains. Lots of fields use this. One way you can make the core equation of reinforcement learning more linear is to use something from mathematics called the Koopman operator. The Koopman operator is a mathematical framework that uses essentially infinite dimensions, basically a lot of space, a lot of flexibility, to take things like basis functions, or however you're trying to get at the dynamics of a system in an abstract sense, and allow you to add them together. And it just makes it scale a lot easier to calculate, a lot more tractable. And hopefully, again, preserves the core true nonlinear dynamics that are in the system. So they use the Koopman operator, make it even better by doing something called a Koopman tensor, which takes the control actions and parameterizes the Koopman operator with those control actions. Again, control actions just mean it's not just the static environment itself. If I interact with the environment changes. And so you're trying to take into account much more realistic information. Pack all that into the Koopman tensor, augment your Bellman equation essentially with that, put it into standard approaches like soft value iteration or the soft actor critic approach, and then go ahead and benchmark and see what's happening. And it looks like it definitely does cause some improvements in the usual reinforcement learning approach. So again, that paper is called Koopman Assisted Reinforcement Learning. You can go check out the code. They have a Koopman RL repository on GitHub. So it's all open source. They tell you the data sets that they use from the Hugging Face repository. And it all runs on CPUs. You don't actually need GPUs to run it. So that's pretty impressive. So go check out the description. You'll see the link to the repo there. You can go try to replicate that yourself or reproduce that yourself. Okay, that was episode 1. Again, I appreciate your feedback. Did it make sense? Am I talking too fast? Is it conceptual enough? Are there some areas you want to go deeper? This is on the app, right? The Papers in a Pinch app. So again, I can't cover everything in every episode. I'm just trying to keep you apprised of the latest research and hopefully give you the conceptual framework to understand it. You can ask questions on the app to me. We can dig a little bit deeper into things. We can maybe throw some equations on there if you want to get a little more technical. That's all fine stuff. But hopefully this is enough to relay to you why this paper just might be important in the field of AI. Okay, thanks so much for listening. And until the next episode, take care.